There is perhaps nothing more satisfying than the sound of shattering glass. We're a race that's obsessed with crashes, right? We go to car races to watch the crashes. Collisions are built into everything we see around us. Virtually every sport has to have some kind of a collision, either between two things, or between two people, or between both. We don't accept a sport if it doesn't satisfy the basic criteria of having at least a few morbid collisions in it. I've always wondered how chess is still a popular sport, right? And once in a quiz I was asked, who's the oldest person to have won an Olympic gold medal and what sport was it? Now, I didn't really know who the person was, but I was pretty sure the sport must have been chess, right? Yeah, and it turned out I was right. So, in the spirit of what we're talking about collisions, let me ask you a question. If I throw a 2 kg ball at you, a heavy ball, and a lighter 1 kg ball at you, but such that the 2 kg ball has a velocity of 1 meter per second and the 1 kg velocity of 2 meter per second, then both of these are coming rushing towards you. Forget gravity for a while, let's imagine you're in space. So, it's only like the balls are coming with a constant velocity towards you. Right? You're grounded somewhere, so you're gonna stop them. Which of these would be easier to stop? In other words, to catch. Now you might argue that both of them have the same momentums. Therefore, it's gonna be equal, right? The amount of force required to bring them to a halt is gonna be the same. Now is that correct? Or now as you think about that question, you freshly graduated after learning about energy in the previous chapter. Now you learned that Newton's second law can be restated in a more useful way as work energy theorem. That's all it was, right? It was a restatement. And here, to deal with collisions, we're going to bring back our ideas of momentum and impulse. But before we do that, what officially is a collision? See, we all know a collision when we see one, but we need a broader definition over here. For us, simply put, a collision is a really, really strong interaction or a large amount of force acting between two bodies for a relatively short period of time. But do you notice something? We are restating Newton's laws, right? But the question really is, when are we choosing to restate Newton's laws and why? The pattern I want you to observe is that whenever a lot of things are varying around, too much chaos, we try and extract something from there that is not changing, is a constant, is invariant. Now, who's the big daddy of all invariants? It's energy. It doesn't change no matter what happens, and that's what we dealt with in the previous chapter. And here, you will learn more about the mother of all invariants, momentum. And you will learn that it's more fundamental than even Newton's laws, even though for our purpose over here, we're going to derive it from Newton's second law. So when do we really need these restatements? We find that when we don't particularly know about the forces, we need the restatements to do the job of Newton's laws directly because we can't directly use them. And when the force varies a lot, we brought in ideas of energy. And we're going to find that when the force acts for a very, very short period of time, we're going to bring in the idea of impulse. Now, in a collision, both these happen. In other words, a large amount of force acts for a really short period of time. So it's time to bring both these ideas together to solve our problems. But before we proceed, let's bring back our general Newton's second law. F equals ma, right? No. That's only when the mass is constant. What's the real law? F equals delta P by delta T, the rate of change of momentum. Correct. Now if you cross multiply, you get F into delta T equals the change in momentum, delta P or P2 minus P1. Now, there are cases where the delta T is really, really small and isn't really meaningful. Say for example, a collision. But the F is really, really large. And it also, by itself, doesn't have too much meaning. But their product, F into delta T, gives you something meaningful, which is a change in momentum. So this quantity ends up getting a name. And what is it? Impulse. So in this form, this theorem is called the impulse momentum theorem. It's going to help us answer questions like if you have your hand over here waiting for a ball that's coming towards you, the mass of the ball is not under your control. The velocity with which the ball is being thrown is not under your control. And the final velocity of the ball is also not within your control, which you have to bring it to rest. You're catching that ball. That's what it means. So then the initial momentum and the final momentum of the ball are not in your control. mv2 minus mv1, which means that the change in momentum is not under your control. So the impulse that you have to deliver is a constant. That's what I'm bringing all this to by our impulse momentum theorem, which means the force you must apply to stop that ball multiplied by the time you need to apply is a constant. F delta T is a constant. Then, if you let that ball come towards you really fast and stop it abruptly and quickly, so the amount of time that you spend catching it is really, really small, then the amount of force you must apply must be really, really large. In other words, your hands will pain really bad. But none of us required Newton's laws to know that if you catch a ball that's coming towards you really quickly, your hands will pain. Right? None of us required that. We didn't have to explicitly know that impulse is being conserved. Right? Even when we were children, we knew that if something is coming towards you really, really fast, and if you want to catch it, then the moment it makes contact, you move your hand in the direction of the ball so that you spend more time catching it. Yeah? Why am I saying this? So that when you're doing this, what you actually did here was you spent a large amount of time bringing the ball's momentum from what it was to zero. In other words, the delta t term was being increased. So as it became more and more and more, the force term had to reduce because the overall product is a constant, the impulse is a constant. So the force you spent or you applied on the ball was lesser. In other words, the pain that you felt would have been lesser. Now, let's ask you another question. You are now good and ready to answer the question that we began this video with, which was, if I throw a 2 kg ball at 1 meter per second and a 1 kg ball at 2 meter per second, which of this is going to be easier to catch? Now, this is an easy question to answer, right? With what you have learned right now, the impulse momentum theorem. If a 2 kg ball is going at 1 meter per second, what's the momentum of that ball? It's 2 kg meter per second, correct? If it's a 1 kg ball going at 2 meter per second, that's also 2 kg meter per second. So both of them have the same initial momentum. And after you catch them, both of them are going to have a momentum of 0. In other words, their final momenta are also equal. Which means the change in momentum required is also equal for both the balls. So which means from what you just know now, you know the impulse you must deliver to stop these two balls are the same. So you can maximize your time if you want to, but whatever you do, for both these cases, you're going to get the same force. Which means it's going to be equally easy or equally hard to catch either of these balls, right? But you've just spent an entire chapter learning about something called the work energy theorem, about energy. Isn't that important at all over here? Now we showed you clearly that the momenta are equal, but what about the kinetic energy? Are they equal as well? Clearly they don't, right? The first ball, the 2 kg ball has, if you try to calculate its kinetic energy, it'll be half into 2 into 1 squared, so you'll get 1 joule of kinetic energy that it has. And what about the 1 kg ball? It'll be half into 1 into 2 squared, which will give you 2 joules of kinetic energy. So the lighter ball actually has twice the kinetic energy, even though it has the same amount of momentum. Now, but the final kinetic energies of both are 0 again. So the change in kinetic energy required for the lighter ball is actually larger, which from your work energy theorem must tell you that the amount of work you must do on the lighter ball has to be more. Right? Otherwise, work energy theorem gets disobeyed. Now, the impulse that you need to give is the same, but the work that you need to do is different. So from the impulse, if you arrived at the fact that both of them require the same amount of force, then what can you infer now? You can infer that if you're applying the same amount of force and you have to do more work on a body, then the displacement required has to be more, right? Because the work done is going to be force dot displacement. But what does it mean to say the displacement required is more? And you might ask, how does it matter, the amount of displacement? Well, let's try and explain that. Let's say that I'm trying to catch the heavier ball with this hand. And I know the impulse I have to deliver is the same for both the cases, but because I have to do some amount of work here, I need to give it some displacement, right? So then the displacement that I need to do that work is, let's say, this much. Now, if I take my other hand and try to catch a lighter ball, then for the same amount of impulse, even if I apply the same amount of force, the displacement I'll require to stop that ball will be larger because the amount of work I need to do to bring the lighter ball to rest is going to be larger. Now, this means for me a larger strain on my shoulders, right? Because the amount of displacement I need is more. Now, if I try to minimize the strain, I have to increase my force and therefore increase my pain. So it becomes a trade-off between the strain and the pain, which makes catching a lighter ball actually harder than catching the heavier ball, even though both of them have the same momentum. So with this example, we've given you a better picture of both momentum and impulse and also of work and energy. So now you know better than even you did before. Now that means that you're good and ready to solve problems involving collisions along a straight line. In other words, one-dimensional or head-on collisions.